Hey folks, in this video I want to talk about the put operation. So up top, I basically have what the API says, right? The put operation, right, in a simple table should put a key value pair into the table. So what does that mean for us? So in our kind of diagrams, we basically have been drawing the keys like this. We have a node, right, and we basically put some value in there. So let's say I put in the value, for example, 15. Right, this would be one thing. Right, or maybe we could put something else in. Maybe we put, for example, a number 1. Okay, so what do we want to do, right? Conceptually, what should we do? So let's say right, I start with, for example, the 15. How would I add it to my tree? Well, I'm going to have to start somewhere. I'm going to start at the root. Right. Overall, my goal here, right, is to add this new node, right, and the node means key value pair to this tree, right. And I want to add to the tree, and I want to keep the tree as a binary search tree. If I add it, somewhere randomly, right, all of a sudden it won't be a BST anymore. It'll be some other tree structure, and it won't do me any good, right. My algorithms will no longer work. If you think back to get, maybe what you may kind of realize, right, is that get actually requires a BST, right? In order for it to make those left-right choices of where it wants to go, it has to be looking at a BST. It can't have an arbitrary tree, right? If it has an arbitrary tree, it'll just get lost. It needs to be, in a binary search tree order. So we want to basically be able to add this node, right, or add this key, in the tree while preserving that BST property. All right. So what do we do here? We have to start at the top, right? Because it's like, well, I only have the root. What else can I do? Start at 8. And then what I can actually give is the following. Just do what get does, okay? Because get basically goes to the place in your tree where the node would be if it was there, okay? And maybe actually I'll change up my case a little bit here. Let's actually change this from a 2 to a 1. That way I have one case of it's there and one case of it's not there. So yeah, right, so imagine how you're doing get on 15. What happens? Start at 8, mismatch, it's too large, so then I'll go to 8's right. So go down to 8's right, that's a 10. The 10 basically, well, that one's also a mismatch. 15 is larger than a 10, go to its right, right? And normally what would happen, right, is I have my X value, right, would trace through the tree, right, in terms of get, and I would end up here looking at a blank space. And I'd be like, well, I don't need to know what to do, right? I'm lost. That's actually perfect for put though, because then put says, you know what? I'm going to add a new node there. Right, I've gone to an empty space, which is a space in this tree that 15 would have been if it was there. It's not there. That means I don't have a 15. So I'll go ahead and put my new 15 there, right? So I've added a new thing there. And it will, of course, be in that BST order, right? Because that's where get would have found it, right? If we're following that original logic. So I end up with my 15 over there. And I have my tree expanded now, right, with that 15 in there. So all is good. All right. Other case, right, is something that does exist in the tree, right? Again, we just do what get does. So get, right, would start at the top for 2, right? So let's say, right, so we did this one, right? Let's take a look now at 2 instead. Start at the top, 2 is smaller, go to the left. Well, mismatch, so go to the left. Compare it again, mismatch, smaller, so go to the left. Then you end up being over here. Well, then I have a match, right? And it's not going to really show up in our diagramming here, but basically, right, if I'm doing a put, right, if I do a put on something that's already in the symbol table, I want to update the value, right? So there would be some value behind the scenes. So for example, right, maybe this thing had the letter A there, right? That was the value of that 2. And over here I have B, right? That's the value associated with the key 2. Well, over here, right, basically what happened is this gets updated, right? So all of a sudden that's no longer an A in there. That would now be a B, right? That would be the job of put, right? So if the key already exists, just update the value associated with it. Versus if the key doesn't exist, you add both the key and the value from scratch into the tree. All right, so yeah, those are the 2 cases for adding stuff to a BST. Let's take a look at the source code. So over here I have, again, 2 functions, right? So it's kind of the same scheme as last time where we had basically the main recursive one and then kind of a helper one. So initially, right, I have this one function or one method, right, that has the key and the value, the things I'm going to add, right? And then I have my helper, which basically adds another thing for that X variable, right? For that little pointer that I'm moving down my tree to go look for where I'm adding something. All right. So one big note here, right, and this is very important for understanding this, right? So we look at this, right? This has a return type of node, okay? So the semantics of this function here is basically, so this thing here, right, this whole function here, what this means is put the node into this tree and return it. So I give it a root, and the return value is a new tree with that node added into it, okay? So I'm basically returning an updated tree, right? And this is going to be important, right? So it's not a void type, right? Some people will go and implement this and they're like, oh, I can do it with a void because I don't need to return anything. No. For this, right, for the way we're implementing it with recursion, we must have a returning a node because it's returning a tree with that new node in it. All right, so looking at the code, we can actually set it almost immediately. Notice the first lines, right? So if x equals null, right? So if I'm asked to put this node into an empty tree, right? Well, if I'm asked to put this node into an empty tree, I don't have to worry about going to the left or the right. I mean, there's nothing to do. So I'll just return a brand new node with my key and my value in it, right? And so that's what this stuff over here does, right? This is basically saying you've asked me to insert into an empty tree. I'll just return you back the one node, right? Which is your now your tree, right? With that node added into it, right? Originally it was null, now it has that one thing, right? It has that one node you asked me to add. All right, so that's kind of an interesting thing there. All right, next thing, right? Basically, this all ends up looking like, well, it looks like compare, right? So it looks like the comparison code inside of the get method. So we basically are looking at, are we looking at the current, are we looking at the key or not, right? Because we're worrying, right? We need to worry, right? We basically need to worry about the case of, oh, it's already there. The basic issue is that we need to worry about, is the key there or is it not there? The case we just talked about, that's the case where the key is not there. But say it is, right? We need to do some comparisons to figure out what's going on. So over here, right, if I'm not looking at an old tree, that means I have work to do. I have nodes to go look at and see if any of them match my key. I start off, right, by looking at basically that current one and comparing its key to the key that I'm looking for. So that's what this is doing over here, right? This is doing the key comparison. And then what we're doing, right, is we're doing the BST rules, right? So if it's smaller versus larger, I go to the left or right side, right? So depending on where it belongs, right? Where is the thing that I want to add? Where should it belong? Does it belong on the left or the right-hand side of what I'm looking at, right? In which case, right, it's like, say over here, right? Say my key, right, is smaller than the one I'm looking at. That means that this item should probably be inserted on the left-hand side of it. So what I do, right, is I basically say, okay, X, right, the thing I'm looking at, I'm going to update your left tree, right? So every node, right, has a left and right subtree. I'm going to update its left subtree to be a new tree with that node added into it, right? So here I did a put on X's left. So the input to that, right, was on the X's left subtree. And I get back from put, right, the return value of this whole side here is basically a new tree based off the left-hand side of that X node with the new thing added into it. And then I'll assign it to X, right? So X basically gets updated, right? We start with its left-hand tree, add a thing to it, and then update it so that it's now looking at the new, updated left-hand tree. So yeah, same thing happens for the right-hand side, right? We basically are doing an update, right? We put in the right-hand side tree, get back out the right-hand side tree with the new key and value added back into it. Other cases, of course, if they're equal, we just update the value. Good to go. We don't need to construct a new node, right? It's already done. The final thing in here is basically to update size. So as you're doing your put, right, you will have taken a node, right, and you have added that node, you will potentially add that node into a tree. If you add the node into the tree, what that means is we need to update that n variable, because that n variable is representing basically the size of that, well, the size of the tree rooted at a particular node, right? Every node carries the size of everything beneath it. And so it's like here, right, we're looking at node x, right? That's kind of our input. And so we update its n, right? So x's n is basically the size of the left side plus the size of the right side plus 1, right? So this is for the actual node, right, you're looking at, right, the root. And then it's like, well, how many nodes on the left child side? How many nodes are on the right-hand side, child side? Add them together, you get the total size of that tree. All right, so there you have it. This is the primary code for doing a put algorithm, right, on top of a binary search tree. If you want, right, you can look at this algorithm again, right? This is kind of another trace from the book. Basically just showing that same get process of going node by node by node to getting to the place the node's supposed to be, right? Either it's there, in which we update it, right? Update its value. It's not there, right? We construct a new node. So yeah, that's the basic way we add nodes to a BST.